All right, so for today, we're going to be going over, like I said, the nervous system first, and then we'll get into the endocrine system after that. And so what we're going to be going over in this first half of the PowerPoint is, we'll talk about the divisions of the nervous system and how we label it so it's easier for us to understand, because there's different parts of your nervous system that are doing different things. Some of it's automatic, some of it's very conscious. Some of it amps things up, some of it calms stuff down. So we'll look at that. We'll also look at the types of neurons. So we will also zoom in like crazy and take a look at what individual nervous system cells look like. We'll talk about how your nervous system actually works in terms of like action potentials and things like that. That one gets a little bit complicated just because there is a lot of like microscopic moving parts there. But hopefully, it won't be too bad. We'll look, we actually will not be looking at like clinical aspects of it. We aren't going to look at like some of these injuries or MS or anything like that. We will talk a lot about like the autonomic parts of our nervous system and how that works, to either amp you up or slow you down. And then we'll talk very briefly about, the structure there of the spinal cord. So, looking at our nervous system, right? If we're gonna, just simply talk about how this works and like what it does, right? The nervous system is a control system, right? It's really like the command center for your entire body, right? It's air traffic control, and so it's this control system that coordinates literally everything that we do, right? It coordinates all of our body's systems. So when you think about that, your nervous system is providing, like NASM defines it in their textbook, as a communication network that runs throughout the body, which is a really good definition if you think about it. Because like if you think about a communication network, it's not just information going away, it's also information coming back. Like I always bring this up when I'm talking about proprioception, which I think we're going to get into today. No, okay, we'll get into proprioception tomorrow. So whenever I talk about proprioception, one of the things that I always try to make really clear is it's like, if I raise my hand and start waving my arm back and forth like this, right? That's my nervous system telling my arm to do something, right? So how does my body know how to control that arm? Like how does it know that it's happening, right? Like, how do I know, or right now, if I'm wiggling my fingers, but I'm not like, I can't see behind me, right? I don't have eyes in the back of my head. How do I know I'm wiggling my fingers? The answer oftentimes is very simply, people go, well, you're the one telling your body to wiggle your fingers, right? And it's like, yeah, that's true. So like, yeah, there's information going away from my brain. So you can assume that it's getting done, but how do I know it is getting done? Right? Like, how do I know I am wiggling my fingers? How does my brain get the information back? Well, that's the other half of your nervous system, right? There's information going out and there's information coming back. And there's this constant, like, processing of information so that your body goes, oh, okay, and it runs it past previous experiences and goes, all right, well, if I'm in this position, I need to contract like this to do this, right? And then it controls us in a different way, right? So there's three main things that your nervous system does. It's not just as simple as like my brain tells my body to do something. My body also like has to interpret that information, and it has to get information back from wherever it's sending information away to. So it really is. It's this very interconnected, incredibly complex command center, communication network. So it detects and responds. It detects stimuli, but it also responds to stimuli, and it carries messages to different parts of your brain. I mean, your brain's got to be able to control your pinky toes, which are about as far away from the brain as you could possibly get, right? And so we do have, luckily, some different divisions. We've got your brain and your spinal cord, which is really cool because that's going to act as sort of a switch center. Your brain and spinal cord are really, really fast traveling. And then what happens is it branches off from your spinal cord to go into the peripheral part of your nervous system so that it can, travel, down the arm, right? So we'll look at sort of how that works today, and then we'll talk about like how nerves are sort of being structured around. But before we get into that, I want to kind of set us up with some animations, as I am wont to do. Let's see, a crash course nervous system. And that's not the one I want, is it? That's the one I want. Here we go.
Get your home and everything in it covered in just 90 seconds.
I will not.
Old insurance kind of sucks.
I'm going to be totally honest with you. I don't really spend a lot of time thinking about my bodily functions, for the most part. Maybe sometimes, but in the next few episodes, I'm going to be talking about all of the organ systems that make our lives possible, even occasionally pleasant. And to start it all off, I'm going to go straight to mission control, the nervous system.
So loud.
Pretty much every single animal, except for some really simple ones, have nervous systems, which is great because it's what lets things do things, like have behaviors. It makes you the sentient living thing that you are. The whole setup here, your brain, your nerves, your spinal cord, everything is made up of specialized cells that you don't find anywhere else in the body. Most of those are neurons, which you've seen them before. They look kind of like a tree with the roots and the trunk and the branches. Neurons bundle together to form nerves, pathways that transmit electrochemical signals from one part of your body to another. So when you bite into a piece of pizza, I love it when there's pizza in the videos. The receptor neurons in my taste buds recognize I'm eating something salty and fatty and awesome, and they carry that information along the nerve pathway to my brain. And then my brain can be like, yeah, pizza. And then it can respond by sending back information through different nerve pathways that say, you should eat more of that pizza. And despite what my brain is telling me, I'm going to try to not eat any more of that pizza. You wouldn't think that it's terribly complicated to know that pizza tastes good and to tell someone to eat more pizza, but it turns out that our brains and our nervous systems are crazy complicated. Your nervous system basically has a big old bureaucracy of neurons, and it's divided into two main departments: the central nervous system and the peripheral nervous system. Central and peripheral. The central nervous system, basically your brain and your spinal cord, is responsible for analyzing and interpreting all of those data that your peripheral nervous system, all of the nerves outside of your brain and spine, collects and sends its way. Once the central nervous system makes a decision about data, it sends a signal back through to the peripheral nervous system saying, do this thing, which the peripheral nervous system then does. Both of these systems contain two different types of neurons: afferent and efferent. Afferent and efferent are biological terms, and they're horribly confusing, and I apologize on behalf of the entire institution of biology for them. Afferent systems carry things to a central point, and efferent systems carry things away from a central point. So afferent neurons carry information to the brain and spinal cord for analysis. In the peripheral nervous system, afferent neurons are called sensory neurons, and they're activated by external stimuli, like the complex and glorious flavor of pizza, and then they convert those data into a signal for the central nervous system to process. The central nervous system has afferent neurons too, and there they bring information into special parts of the brain, like the part of the brain that goes salty. Efferent neurons carry information out of the center. In the peripheral nervous system, they're called motor neurons because many of them carry information from the brain or the spinal cord to muscles to make us move, but they also go to pretty much every other organ in your body, thus making them work and do stuff to keep you alive. In the central system, efferent neurons carry information from special parts of the brain to other parts of the brain or spinal cord. Of course, if it ended there, it would be way too simple, and no good bureaucracy has just two departments. So the peripheral nervous system is actually made up of two different systems with two very different jobs: the somatic nervous system and the autonomic nervous system. The somatic system controls all the stuff you think about doing, like all the information coming through your senses and the movement of your body that it makes when you want it to make movements. So here's something interesting. Since we're totally in love with our brains as sort of the center of all being of ourselves, we think that all the information about everything going on in our bodies goes to our brains for some kind of decision. Not so. Sometimes, like when we touch a hot stove, the afferent neurons carry the signal hot to the central nervous system, but that information doesn't even ever get to the brain. The spinal cord actually makes that decision before it gets to the brain, sends a message directly back to the muscles saying, get your hand off the freaking stove. This bit of fancy nerve work lets the spinal cord make decisions rather than the brain, and it's called the reflex loop. So the other branch of the peripheral nervous system, the autonomic system, carries signals from the central nervous system that drive all of the things that your body does without thinking about them: your heartbeat, your digestion, breathing, saliva production, all of your organ functions. But we're not done yet here. We need to go deeper. The autonomic nervous system has two divisions of its own, the sympathetic and the parasympathetic. And the jobs that these two perform aren't just different, they're completely opposite. And frankly, they're always vying for control of the body in some kind of nervous system cage match. The sympathetic division is responsible for freaking out. You've probably heard this talked about as the fight or flight response. In other words, stress. But stress isn't all bad. It's what saves our lives when we're being chased by saber-toothed tigers, right? The sympathetic system prepares our body for action by increasing the heart rate and the blood pressure, enhancing our sense of smell, dilating the pupils, activating our adrenal cortex to make adrenaline, shutting down blood supply to our digestive and reproductive system so that there'll be more blood available for our lungs and our muscles when we have to like run. And even though you're not in a constant state of panic, at least I hope not, I kind of am, that system is running all the time, every day. But right next to it is the parasympathetic division, working hard to make sure we take it nice and easy, dials down the heart rate and the blood pressure, constricts our lungs, makes our nose run, increases blood flow to our reproductive junk. Our mouths produce saliva, encourage us to poop and pee. That's basically what we have to thank for taking a nap, sitting in front of the TV, going to the bathroom, and getting it on. So consider yourself lucky you got both the stress response and the chill the heck out response working side by side, because together they create a balance or a homeostasis. Now, that's what the nervous system does. Next, we have to talk about how it does it. The neurons that make up our nervous systems make it possible for our bodies to have their very own little electric systems. So to understand how they work, you have to understand their anatomy. Like I've said before, a typical neuron has branches like a tree. These are called dendrites, and they receive information from other neurons. Neurons also have a single axon, the trunk of the tree, which is branched at the end and transmits signals to other neurons. The axon is also covered in a fatty material called myelin, which acts as insulation. But the myelin sheath isn't continuous. There are these little bits of exposed neuron along the axon, which have the sweetest names in this whole episode. They're called the nodes of Ranvier, which seems like an excellent working title for the 8th Harry Potter novel, Harry Potter and the Nodes of Ranvier. Anyway, these nodes allow signals to hop from node to node, which lets the signal travel down a nerve faster. This node hopping, by the way, has a name. It's called saltatory conduction. Conduction because it's electrical conduction, and saltatory because saltatory means leaping. Finally, the place where an axon's branches come in contact with the next cell's dendrite is called a synapse. And that's where neurotransmitters pass information from one neuron to the next. Now, think back to, or just go watch the episode that we did on cell membranes, where we talked about how materials travel down concentration gradients. Well, in much the same way, all of the neurons in your body have a membrane potential, a difference in voltage or electrical charge between the inside and the outside of the membrane. You might also remember that this buildup of voltage is handled in part by a sexy little protein called the sodium-potassium pump. Basically, the pump creates a voltage differential like charging a battery by moving 3 positively charged sodium ions out for every 2 potassium ions it lets in, creating a net negative charge inside the cell relative to the outside. When a neuron is inactive, this is called its resting potential, and its voltage is about negative 70 millivolts. But in addition to the pumps, neurons also have ion channels. These are proteins that straddle the membrane, but they're a lot simpler and don't need ATP to power them. Each cell can have more than 300 different kinds of ion channels, each tailored to accept a specific ion. Now, don't zone out here, because all of this stuff has got to come into play when a neuron becomes active. This happens when an input or stimulus creates a change in the neuron that eventually reaches the axon, creating what's called an action potential, a brief event where the electrical potential of the cell rapidly rises and falls. When an action potential begins, like when a molecule of sugar touches one of my sweet taste buds, some ion channels open and let those positive sodium ions rush in so that the inside starts to become less negative. With enough stimulus, the internal charge of the neuron reaches a certain threshold, which triggers more sodium channels to respond and open the floodgates to let even more ions in. That's happening on one tiny little area of the neuron, but this change in voltage creeps over to the next bunch of sodium channels, which are also sensitive to voltage, and so they open. That exchange triggers the next batch and the next batch, and so on down the line. So the signal of changing voltage travels down the neuron's membrane like a wave. But remember, the myelin sheath insulates most of the neuron and just leaves those little nodes exposed. So instead of being a steady wave, the wave jumps from node to node, speeding up the travel time of action potential down a neuron. That's your saltatory conduction at work. When the wave reaches the end of the neuron, it triggers a release of neurotransmitters from the neuron through exocytosis, and those neurotransmitters then flow across the synapse to the next neuron, where they trigger another action potential over there. And by this time, so many sodium ions have gotten inside the first neuron that the difference between the outside and the inside is actually reversed. The inside is positive and the outside is negative. And it seems like neurons hate that more than pretty much anything else, so it fixes itself. The sodium channels close and the potassium channels open up. The positive potassium ions rush down both the concentration and electrochemical gradients to get the heck out of the cell. That brings the charge inside the cell back down to negative on the inside and positive on the outside. Notice, though, that now the sodium is on the inside of the cell and the potassium is on the outside. They're in the opposite places of where they started, so the sodium-potassium pumps get back to work, burn up some ATP to pump the sodium back out and the potassium back in. And whew, things are now back at the resting potential again. So that, my friends, is how action potential allows neurons to communicate signals down a whole chain of neurons from the outer reaches of the peripheral nervous system all the way up the spinal cord into the brain and then back out again. So let's zoom out. Look at the broad view here. I'm going to take a bite of this pizza. All my taste buds have neurons in them. Each of my taste buds contains between 50 to 100 specialized taste receptor neurons. Chemicals from this beautiful pizza dissolve in the saliva and then stimulate the dendrites on the afferent neurons. This generates a bunch of action potentials that travel from the afferent neurons in my tongue all the way to my brain, which is like, my goodness, I think that's pizza. Let's have another bite. The brain then sends messages through the efferent nerve pathways to do all sorts of things. One, chew, which involves constricting the muscles in my jaw over and over again. Two, lower my head down to catch another bite, which involves moving all kinds of neck muscles. Three, swallowing, which involves constricting the muscles in my throat and esophagus. Four, opening my mouth again to receive another bite. That signal is also going to my jaw. And that's not even to mention what's going to go on with the digestion of this bad boy driven by the autonomic nervous system. But digestion is still a couple of episodes now. Hopefully, there will be more pizza. Thank you for watching this episode of Crash Course and for giving me an excuse to eat more pizza. If you want to review what we learned in this episode, check out the table of contents. Thanks to everyone who put this together. If you have questions for us, Facebook, Twitter, or the comments below. We'll see you next time.
Okay, so like I said, there's a lot of like itty bitty working parts in our nervous system, and one of the hardest parts to understand about it is when we look at those action potentials. So we're going to look at that in detail today to understand like how we are generating that electric charge, right? That action potential. So looking at the nervous system, right? Again, we're going to divide it into divisions so that we can understand it. This is just going to make it a lot easier for us to label things and understand like what pieces of function are. So this is a really great way that they've labeled this. In your notes, I recommend, if you're copying your notes, I recommend doing them the way I've got them laid out here. Woo! Where you can see we've got the central and peripheral, and then the peripheral will divide into these two, and then one of those is the autonomic, and the autonomic will divide into these two. Alternatively, you will often see it labeled out as a chart like you saw him do. You saw like in the video, you'll see you'll have your central nervous system, and you will have your peripheral nervous system. And they're kind of like, you know, these are very linked together, you know, like these are really just like one chunk. But your peripheral, which is, you know, all the stuff that branches out from your central nervous system, this is going to split into two sort of different divisions here, right? We're going to split this into our I'm going to put autonomic nervous system. So the autonomic nervous system is the automatic stuff. This is the stuff that you don't really have any control over, right? Like this is the stuff that kind of just happens without you really having to think about it. Like, you know, if you've got, you know, breakfast sitting in your gut right now and your stomach is working away, churning at it to process that stuff, you know, that's part of your autonomic nervous system. Your brain is controlling, you know, the little muscular contractions that are happening in your stomach. It's going to control the sphincters that open up to let that food into your small intestine, and then the peristalsis, little contractions that take place in your small intestine to move that food through the whole intestine until eventually it gets to our large intestine and then works its way out of the body. All those little contractions are controlled by your nervous system. They're just happening in the background autonomically, right? We don't really have any control over that. And then there's the somatic nervous system, which is the one that we tend to think of when we think of our nervous system, right? Like this is the one that most people are somewhat familiar with, because this is your conscious control. Like me raising my arm right now, that's somatic. Me talking right now, that's very somatic. I have control over that, right? But there's two types of autonomic reactions. Your autonomic reactions are going to split. They're going to divide into two other divisions, and you're going to see either your sympathetic or your parasympathetic. And your sympathetic nervous system is the section that is responsible for basically freaking out about stuff. So like your sympathetic nervous system is your fight, or he mentions in the video, it's your fight or flight system, right? So this is the, we'll say sympathetic nervous system. And then we'll see your parasympathetic, right? So it kind of divides down like this, right? So your parasympathetic nervous system is responsible for basically freaking out about stuff, and your sympathetic nervous system is responsible for freaking out about stuff. Your parasympathetic nervous system is responsible for calming down after it's done freaking out, right? So all of this is under control of like the central nervous system, which is your brain and your spinal cord. But your brain and your spinal cord can't directly interact with the rest of your body. So it hands the information off to your peripheral nervous system, where, you know, then your nerves branch off and then they get to whatever site it is that they're affecting. If it's your digestive system, great. If it's your, you know, quadriceps muscles, awesome, right? But it's going to travel down from your brain, and then it's going to branch off of your spine. And then you're either going to have autonomic reactions like those in your digestive system, or you're going to have somatic reactions like those in your muscular system. Now, the autonomic reactions that you don't really have control over are often sympathetic, like I said, which is going to be the fight or flight system, or it's going to be the parasympathetic, which is known as the rest and digest system, right? So the autonomic reactions, you're either going to freak out about something, right? Or your parasympathetic nervous system is going to calm you down, right? This is actually why you guys might have, I don't know if you've ever noticed this, but if you've ever been doing a relatively like tough workout where you've really been hitting it kind of hard, you don't really often feel like you have to go to the bathroom that much, and you often don't get that hungry during like very intense styles of workout. This is actually why exercise is considered, and this shocks people when they hear this, but exercise is actually considered an appetite suppressant, at least temporarily. Now, after you are done exercising and your body's like, your sympathetic nervous system's like, are we good? And then your parasympathetic nervous system starts to activate, and it's like, we're good, calm down, relax, right? That's where all of a sudden your skeletal muscle loses a little bit of blood flow, it loses a little bit of electrical activity, it starts to calm down. Meanwhile, your digestive system starts to turn on, and, you know, starts to do all of its intense work. And that's where it's like, oh my God, I'm actually, you know, I could really go for a post-workout meal right now, you know? So those are the divisions of our nervous system, kind of laid out in chart form here, which I like. But you are also, you know, I also really like sort of the note version here. But each branch is sort of underneath another branch. And one thing NASM loves to do on their questions, and I just want to point this out now, NASM loves to ask you, you know, which of the following, like questions where it's like, which of the following parts of your nervous system are considered involuntary? You know, which when you hear involuntary, you should automatically be thinking autonomic, right? But they also really like to give you, like, they like to give you 4 options where they'll say peripheral, which is not the right answer because that can be autonomic or somatic. They'll say somatic, which we know is not the right answer. But every now and then they'll say like the sympathetic nervous system. And the sympathetic nervous system is autonomic. You don't have any control over it. Even though we tend to go like, oh, it's autonomic, and we just kind of jump straight to that answer. Remember, both sympathetic and parasympathetic fall under the autonomic category. So they love to do that one. It's like a fake trick question. It's not really a trick question. It just is, slightly more complex than if they were to ask you outright. So let's talk about what these divisions are. And we've already been kind of talking about it a little bit, but the central nervous system is responsible for coordinating all the signals, right? This is your brain and your spinal cord. This is, like I said, this is your command center. This is air traffic control. This is the main part of your nervous system where all of your conscious, very complex thoughts are taking place, right? But we're not able to get information out from our central nervous system directly to our muscles and glands and digestive organs and things like that. So instead, we have to have nerves that branch out from there. And that is the parts of your peripheral nervous system. And your peripheral nervous system is responsible for carrying nervous signals throughout the body, whether it's going towards the central or away from the central, it doesn't matter. That's going to be the peripheral part. Think of it as like it's in the periphery, right? It's around it's around the center. And so it consists of like your cranial nerves, which are, from your brain, there's some nerves that branch out on top of your skull and stuff, but also your spinal nerves, which are probably the nerves that most people are kind of picturing. But if we look at like central versus peripheral nervous system, and I know there's a picture coming up in the PowerPoint in just a second, you can kind of see the two different divisions here, right? Your central is in white here. It's the brain and spinal cord. And then look at how many, all these nerves that are branching out from your spine, right? Some that travel down your arm, some travel down your leg. Anybody in here ever struggle with sciatica? Anybody ever get like a shooting leg pain that travels down their leg? Sometimes it's called piriformis syndrome. Sometimes they call it sciatica. It's a very common condition that a lot of your clients are going to struggle with. This is something we want to be pretty familiar with, actually. But what sciatica is, there's a bundle of nerves right down here at the base of your spine called your sciatic nerve. And there's a muscle called your piriformis, which runs from your sacrum over to your femur. And it can sometimes get really tight. And when it gets really tight, it starts poking that bundle of nerves. And so what people will say when they have sciatica, they'll describe it as a shooting leg pain. They'll describe it as like a pain signal that will run down their entire leg, which makes sense because this bundle of nerves gets pinched as it travels down. And so the whole thing, is very painful. You don't want to touch your nerves. That hurts. So that is sort of the divisions of our nervous system here. And again, you can kind of see there's the brain and spinal cord, and then there's all of these nerves that are kind of bundling out and branching away from our peripheral nervous system. Now, in that peripheral nervous system, you've either got control over stuff or you don't have control over stuff. You've got your somatic nervous system. This is voluntary control, right? Me controlling my vocal cords right now, me choosing to take a breath in, right? That's a somatic contraction using secondary respiratory muscles. This controls movements, right, generally, but anything that's very conscious is part of your somatic nervous system. But anything that's not conscious, like your heart, for instance, you have no control over your heart rate. And I know that, like, I've had people argue with me on this before. It's like, I practice this and I know how to slow my heart rate down. Yes, you do. That does not mean that, like, you being able to slow your heart rate by picturing yourself breathing calmly on a beach or, petting your cat or something, like, just because like you can do certain things that slow your heart rate down does not mean that you have control over your heart rate. Like, you cannot go, all right, heart, I want you to beat right now. Right? Like, you can't do that. We don't have the ability, right? Because it's part of our autonomic nervous system. So your smooth muscle, which is all of your organs, your cardiac muscle, which is your heart, and then different glands that are running throughout your body are all autonomic. For instance, like, in the video he was talking about like pizza. I want you guys just to take a second and picture your most favorite pizza here in LA. Like really just like salty, delicious, your favorite pizza you've ever had in your life. Really picture it as if it's in your mouth right now. Chances are your mouth started watering when I started describing, I know mine did, and I was literally just, I was the one describing it. And I've done this a million times. But if you really take a second to really remember what that pizza tasted like, you kind of tricked your brain into thinking that you were about to take a bite. So your body like salivated to kind of get ready for that bite. That is your autonomic nervous system. You don't have any control over stuff like that. And that was a gland underneath your tongue that spits all that spit out. Then your autonomic section is going to divide into either a sympathetic nervous system or a parasympathetic nervous system. The sympathetic nervous system is the fight or flight responses, right? So this is the stuff that's responsible really for freaking out. It amps up certain body systems. So when your body needs to make adrenaline or cortisol or any of these stress hormones that help our, body function like physically or respond to stress in a really positive way, that's your sympathetic nervous system. And then your parasympathetic nervous system is the rest and digest system, right? This is responsible for calming you down so that you can like process all of that stuff. Your parasympathetic nervous system is what helps you fall asleep. But it's interesting. You look at like overtraining, right? So overtraining is something we as trainers always have to be a little worried about for our clients. We got to make sure that we do not overtrain our clients because they're likely to get injured. And one of the ways that we look for overtraining is if at the end of a workout routine, their heart rate does not decline back to normal, or in between sets, their heart rate just stays elevated rather than like declining back to normal, that's a sign of overtraining. And basically what it's showing you is that their sympathetic fight or flight nervous system is so kicked on and so freaked out because they are pushed to the point of overstressing that their body is just not turning off any of the stress responders. They'll often describe it as like a loss of appetite. They'll sometimes describe it as having trouble sleeping. All of those things. And you would think like, what do you mean you're having trouble sleeping? I've got you on a really hard workout routine. You should be exhausted and ready to fall asleep. Yeah, they are super exhausted and they are, it would be great if they could fall asleep, but there are so many sympathetic stress responses running throughout the body that it is keeping their body awake because it's like, their body is like, we've been fighting bears for the last 90 days, it's just like, and I won't sleep until I'm dead. It's like this way overstressed situation that's not very good for us. So that's your fight or flight nervous system. And then your sympathetic, like I said, that's your rest and digest. So looking at the functions of your autonomic nervous system and sort of how this works, right? Like I said, the autonomic nervous system, this is going to be all regulating your glands, smooth muscle, like organs and stuff. Blood vessels, that's a really big one. I mean, how do we control, if I want to make sure that I can work out really effectively, I don't need to worry about like my digestive system getting a lot of blood flow. I don't need my digestive system doing very much work right now. I want all of my work being dedicated to my, skeletal muscle, the muscle that's helping me, get that barbell up off the ground. So I want to shut down blood flow to my digestive system and increase blood flow to my skeletal muscle, which is a very autonomic response. So the blood vessels as soon as I start like lifting a heavy weight, our body will constrict the blood flow by constricting the blood vessels to like things like my stomach and my small intestine. And then it will expand the blood flow to things like your skeletal muscle. And you guys have all seen that probably if you've ever been like working out like crazy and you look at your arms and you see like you're very vascular and stuff. That's your blood vessels just opening up in response to get you ready for an intense workout, right? And then, like I said, that is going to split into the sympathetic and the sympathetic and parasympathetic. Sympathetic is responsible for triggering things into like high alert, right? Like I said, it's your flight or flight. So your endocrine system releasing adrenaline, that's a fight or flight response. We're going to talk about hormones at the end of this PowerPoint, but hormones are really intense and they're kind of slow to respond. So oftentimes when you do create like adrenaline, the problem is it's still running through your blood. Even if you're in a place where you want to calm down, maybe the danger is over, but you're still sitting there like, what's next? And it's like, nothing's next, calm down. That's because your sympathetic nervous system tends to work together with your endocrine system to create these like stress hormones. And stress hormones are intense and kind of slow. So that takes a little while to kind of flush all that out of there. And then like I said, we have our parasympathetic nervous system, which is responsible for helping us return to normal. Generally, these have the exact opposite effects of things, you know. You can even look at it in terms of like your blood sugar levels, right? When your blood sugar levels are elevated, right, your body needs to produce insulin to get that sugar out of your blood. The exact opposite is true in terms of like if your blood sugar levels get too low, your body will have to release a different hormone in the form of glucagon to raise your blood sugar levels back to normal. Both of those are, you know, intense responses, right? It's going to be a parasympathetic nervous system response to get you to recover, you know, to rest and digest that sugar. So producing insulin is a parasympathetic response, but releasing glucagon because your blood sugar levels are really low and you need blood sugar is actually a sympathetic response. That's why it does not feel very good. That's why you sometimes get really hangry when you're low in blood sugar. You know, you're like, it's because your body is also creating like other stress hormones because it's like, yeah, we don't have any freaking food. I'm stressed out, right? Like, I don't know if we're, you know, if we're in a plane crash or something, or we're on the island from Lost, like what's going on, you know? So your body sort of goes through that stress response. All right. Any questions on the divisions, guys? Any questions about how that works or how those are divided up?
I'm good.
All righty. Well, let's take a look at the neurons. Let's zoom in and take a look at these cells individually, right? We looked at muscle cells, we looked at bone cells, right? We talked about our osteons like osteoclast and osteoblast. We looked at actin and myosin fibers inside of a muscle fiber, right? So now let's take a look at a neuron, right? So the neuron is the functional unit of the nervous system. It's because neurons are shaped the way they are able to function in such a way to give us this amazing communication system, right? Just like the way that a muscle fiber, which is a muscle cell, has the sarcomere. And the sarcomere is the area where like actin and myosin are overlapping, right? That sarcomere is the functional unit of the muscular system. Thanks to muscle cells being shaped the way they are able to function a very specific way. So looking at the neuron, right? These are the cells that coordinate and make up like our nervous system signals. So they're really specialized, like any cell inside the body, right? To be able to coordinate those signals. And so they have a lot of sodium, potassium pumps in them. And when you look at their shape, they've got these, you know, big fingers that branch off from them this way, and then these big long tails that branch off from them this way that also end in little fingers. And so that's what's so good about creating this like network, right? You're plugging this into that, into this, into that, you know? And so when we look at this, if we're looking at like labeling out like the sections of our cell, we're going to see a lot of the normal cell properties here, you know, nothing too surprising, right? We are going to see we've got the cell body, just like, you know, covered in a membrane, just like any other cell. We're going to see a little nucleus in there, right? We're going to see lots of mitochondria running throughout the cell, lysosomes, centrosomes, all that stuff, right? All the normal stuff we're going to see. But let's talk about the special stuff. What is it that makes nerve cells different than other cells? What makes neurons unique? Well, they have these what are called dendrites. And dendrites are the little fibers that carry impulses to the body of the cell. Okay, so when we look at like little dendrites, they're these little fingers. And let's say you had another nerve cell like over here, right? And then that like reached down and it attached to the little dendrites here. Well, now if a signal traveled from that neuron over here and touched this one, it can then travel to the center, and then that can act as a switching center to either go up this way and travel to like the next neuron, or it can travel down this way to travel this way. You know, it can get this one, or it can travel down to that one, right? So it's got different ways that it can go and do different things. And so dendrites, like I said, they carry the information towards the cell body. They act as the arms that attach and they synapse, meaning they connect with other nerve cells and other structures inside the body. So, you know, this is where you are like sort of grabbing and creating a connection point. Then there is also the axon, which is this big tail right here. And they carry impulses away from the cell body, right? So this is actually kind of, it's funny if you look at this, right? Like your neurons are shaped or function kind of similarly to your nervous system, right? We as people, like let's say we touch a hot stove, right? Your hand is going to take information in, and then it's going to take that information and send it to wherever it needs to go to recruit the right muscles to pull your hand back, right? Like information is going to come from my fingertips, go to my brain, and my brain's going to go, whoa, that's not good. Then it's going to send that signal back down and contract my bicep to pull my elbow away, right? Kind of similar to the way the neuron itself is shaped. And so axon fibers carry impulses away the same way that dendrites carry information too. Now, on your axons, we really want to make sure that that nerve cell is protected, especially if it's a very, very, very long nerve cell. So like, longest nerve cell. When you look at some of these nerve cells, the longest one, wow, oh, that's so cool. They can see like the one in a brontosaurus. That would be amazing. Sorry, that's very distracting. So one of the longest cells you've got in your entire body is actually that sciatic nerve that we talked about, the bundles that branch down from the sciatic nerve. And so it travels basically the length of your entire leg. And it's this big freaking long tail that's coming off from here, right? And so that tail, that is sending this really long signal. We want to make sure that that signal does not get interrupted. That's really, really, really important. So because of that, your body has this really cool protective mechanism called myelin. And you can actually see that right here. See these little like lumps that are forming on the neuron, right? That is your myelin. And if I look at, if we look at myelin, it kind of looks like this when it's shaping itself around. They're actually their own individual cells that live on your regular neuron cell itself. Sorry, no, kill me. So you can see like there's the actual axon right there. And what'll happen is, and they call this a Schwann cell, but basically the myelin will wrap itself around and around and around and around. And this protects that signal from ever losing, these are electric signals, right? This is electricity and there's fluid everywhere. And electricity just wants to travel to wherever it can get to, the fastest. And so luckily myelin is mostly made up of fat, actually. This is why having fat in your diet is so important to maintain your nervous system. And so this fatty material is going to protect that signal and keep it from leaking out this way or that way or whichever way, right? So that's what we're going to see around our axons. We're going to see this myelin sheath, right, which is this special type of cell that insulates and protects your axons so that the signal doesn't get lost. But I will say, and he mentioned it in the video, you'll notice that they have these little gaps in between them, right? These little gaps from place to place to place. That gap is actually really important because that actually, like I said, electricity wants to travel to wherever it can get to the fastest. And so if it actually does have this little gap right here, what'll happen is the electric signal will jump across the gap and then it'll be protected again, like once it gets to the other side. But that big jump speeds up the signal, right? It's kind of it's like sometimes when you're watching when you're watching baseball, right? Sometimes like it's faster to throw from like one person to the next person rather than do a big long like lob throw, right? So if you do this like little like quick pass and then that person's able to turn and do another quick pass, you're much more likely to get like a double play than you are if like you're tossing this big long throw, right? Or you can imagine it as like you got a bunch of people like lined up and they're going to pass one thing from one person to another person. At some point if you were to like space people out to where they can't hand it to the other person but they have to throw it, it's going to travel much faster, right? As long as nobody drops it. And if anybody does drop it and that signal gets lost, that is a disease that we call multiple sclerosis. Right, I might mention that at the end of the PowerPoint just because it's a pretty specialized disease, but sometimes you'll see it in the gym and stuff. Any questions about myelin or anything like that, guys? Looking at axons, any questions there? Cool. So there's the myelin sheath. Now, let's talk about the types of neurons. And this is probably, I would say, this part is the part that's, I'd say, most likely to show up in your regular in your test. So the types of neurons we got, it's either you're either going to see like these types of neurons, or you're going to see the function of these neurons. These are the way they like to ask these questions. But the types of neurons you got three major categories of neurons. Okay, they're labeled after what they do. So you have got sensory neurons, which are known as afferent neurons, right? And by the way, like afferent and efferent, I'm just apologizing on behalf of biology teachers everywhere. Sorry, they sound so similar. This is like when you were in English. I don't remember this from like English, being in school and stuff. You had to learn the difference between like affect and effect. And your teacher was like, yeah, so when you're writing it, like affect means this and effect means this. And you're like, what was that? Like, I'm sitting in the back. Like, I can't. Gotcha. Thanks, Andres. Like, you're like, what? That sounds exactly the same to me. No. But there is, I'll try to be as clear as possible. We've got afferent neurons, which are affected by stuff, and you've got efferent neurons, which are affected by stuff, right? Or effect stuff, I should say. So sensory neurons, afferent neurons. These are neurons that are going towards the brain. Think of that. I mean, honestly, sensory is a much better term here, right? Because their job is to sense stuff. So they come from an effector site and they go to the brain, right? So they are often like affected by something. So when you are cold, you are being affected by the temperature. That's why they are afferent neurons. You're being affected, right? They sense temperature or pressure or touch or whatever. When we think of like, you remember this from our, I know the three of you guys have been through program design. When you think about like muscle spindles, right? Remember, muscle spindles are those sensory neurons that run from the end of a muscle fiber to, or I'm sorry, from the end of one muscle to the end of the other, like the other end of the muscle, right? So their job is to sense how long the muscle is, right? That's a sensory neuron. That's what a muscle spindle does. It tells the brain, hey, the bicep, I'm wearing this big thick sweatshirt, the bicep is, mostly shortened right now. We are at like, about as short as we're going to get. But if I go here, right, now that's going to send a signal in my brain saying, hey, we're being pulled apart, right? Like that's what my muscle spindle does. It tells my brain if I'm in this position or if I'm in this position, right? And so that's a sensory part of your nervous system. So sensory neurons do that. They're responsible for gathering information. If your brain is sending an inquiry, it's like, hey, how long is the biceps muscle right now? It wants to get the information from a sensory neuron. Now, the exact opposite of that are motor neurons. Motor neurons, or efferent neurons, they have an effect on this world. You are going to have an effect on something because you are going to pick something up, move something around, shake something, whatever, right? So motor neurons are neurons that conduct impulses to either muscles or glands. Their information is going away from the brain, right? So this is going from the brain to an effector site rather than coming from a site and going towards the brain. So this is responsible for sending information away in order to like recruit muscles, right? So if my muscle spindle is being stretched like crazy, right? It's being pulled apart, it's about to rip, right? My muscle spindle, which is a sensory neuron, sending all this information to the brain saying, hey, we are maxed out in terms of length right now. Do not stretch any further, right? And then my motor neurons actually might have, my body might automatically contract a muscle in order to like pull it back and shorten it. This is what we see a lot of times in overactive muscles. So take a look right now, right? Let's say I do this, right? Let's say I'm standing here. I'm gonna stretch my left leg out like this. I'm gonna keep my foot flexed back. Can you see that? I'm going to keep my foot flexed back. That action right there, keeping my foot flexed back, is stretching my calf muscle. And because I've got a nice straight leg right now, I'm also stretching my hamstring muscle. So now both of these are stretched. And if I create a little bit of an anterior pelvic tilt, that's even going to further stretch my hamstring muscle. So if I start to hinge at the waist right here, I'm starting to get a really deep stretch in my left hamstring. And if it gets really intense, I'm like, God, that freaking stretching, all of a sudden my knee buckles, right? And that buckling action of my knee is a protective mechanism that my body has designed in it, where it will contract a muscle rather than continue to lengthen it, because if it continues to lengthen it, it might tear in half, right? This is why when you see some people doing certain exercises, like picture the Frankenstein straight leg kick, right? Where they're doing that like left and then right, and they're walking with the big straight legs, right? You'll sometimes see people's knees just buckle like crazy, and they'll bend their knees. They're bending their knees because sensory neurons are saying, hey, do not kick with a straight leg. You're going to rip us in half, right? And then motor neurons are contracting that muscle in order to keep it from being fully stretched out. Now we use different methods, like autogenic inhibition and reciprocal inhibition, things like that, to stop this process and hopefully turn this off so that we can, fully keep the muscle nice and stretched out and get a nice range of motion. But that's how your nervous system is arranged, right? You've got the sensory neurons getting information, you get the motor neurons, which is like, responding to that information. And then we've got interneurons, which are the neurons that are basically relaying information from place to place to place to place to place. We don't have one nerve that runs from the bottom of our foot all the way up to our brain. So instead we have, we're going to pass the information off, right? And so, if you're going from neuron to neuron to neuron to neuron, those are your interneurons, right? They're responsible for sending everybody. This is like, if you sent a letter to someone and they sent a letter back, all the post carriers that it passed hands through on the way there, those are your interneurons. So that is your nervous system, how it is sort of arranged very, very simply. Now, there's a lot of different types of neurons. One of the things that we got to talk about is what's called neuroglia. Neuroglia is really cool. These are basically all the special little nerve cells that you've got in your system that are not doing exactly the same thing. They're not necessarily direct neurons that are acting as sensory neurons or as motor neurons or anything like that. These are all the special other types of cells that happen to exist in your nervous system. We used to think they were really unimportant. We used to think they didn't really do much, but we're finding that they can do more and more and more all the time, the more we learn about the nervous system. But they're protecting your nervous system. They're repairing your nervous system. They're sometimes acting as like your immune system to like kill invaders and things like that. But like Schwann cells, we looked at like the myelin earlier, that's actually an example of neuroglia. There's also really cool ones called like astrocytes, which you can see here. Astrocytes are actually allowing you to like have a stronger connection between like a regular neuron and a capillary, the little blood vessels there. And then if you have like a neuron that dies, sometimes astrocytes and neuroglia, they can actually come along and pick up the slack. They can start acting like regular neurons, which is where you'll hear these stories about people who had a stroke, and unfortunately they didn't get any blood to a certain part of their brain, and so that part of their brain suffocated and those cells died, and they're really not coming back. But other cells in the area started kind of rewiring themselves and relearning things. And so you'll hear about like, this is why you'll hear these crazy stories sometimes, where like people will have a stroke and then all of a sudden their personality will be a little bit different. It's because different nerve cells are getting used. Or you'll hear about like, all of a sudden they, were an amazing artist. Like here, let's see if I can find this interesting story. Man has stroke and then becomes artist. I think it was a guy. Yeah, this guy like, just became like a major, look at his t-shirt. That is actually terrifying. But you'll see this sometimes. You'll see people be in like an accident where a part of their brain will get damaged and it will completely, totally, absolutely change like their entire personality. What is this? What for? He's a repairman, and then he became an artist. Crazy stuff. There's millions of stories out there on the internet of stuff like that, where you'll hear these really interesting stories about people who, part of their nervous system got damaged and then their brain just rewired itself to learn how to do something else. So next thing we got to look at, so we got to remember that our nervous system is doing all of this work. All of this work is happening because of a series of electrochemical signals. We call it electrochemical because we are using chemicals to create electricity. You know, you are basically a sack of batteries, you know? And so we've got all this sodium, we've got all this potassium, and we've got all this fluid that makes it easy to move sodium and potassium throughout our body. And sodium and potassium have different levels of electric charge. They have different, you know, different levels of electrons surrounding their atoms. And so if you have a bunch of positive stuff over here and a bunch of negative stuff over here, and you use a little bit of cellular energy to like flip those things, and now you've got like mostly positive stuff over here, but this one little bit of negative, and then mostly negative stuff over here, but this one little bit of positive. Remember what I said, if you ever want to understand how the universe works, remember this constant. Nature hates gradients. Nature does not like stuff mixing. It wants everything nice and separate, everything very even, right angles, you know? And so what happens is like nature is going to naturally want to flush those concentrations back to normal. Wants all the positive stuff back over here, wants all the negative stuff back over there. And so when that happens, the electrons that are like surrounding the atoms of sodium and surrounding the atoms of potassium that get moved around creates electricity. We get this electric signal, right? And so our nervous system uses that arrangement to basically pass an electric signal from here down to there, wherever it happens to be going, right? And so your nervous system works by means of electric impulses sent along fibers, those are your neurons, transmitted from cell to cell to cell at little junctions. We call those junctions synapses, right? Remember a synapse, we looked at like muscular contractions, where we talked about the neuromuscular junction on Friday. That area where they meet, that's a synapse, right? Like it sits in like that, and it releases those chemicals, and then those chemicals bind with the muscle cell, and then the muscle cell, it creates an action potential and does the exact same thing. It generates its own electric potential. That was a synapse, right? It's where anytime a nerve cell interacts with something else, we call that a synapse, even if it's another nerve cell. So normally it's sitting at like a resting state, you know, like your cells are mostly just sitting around. They've got a good concentration stored up, and they're just kind of relaxing, you know. So your membrane is polarized, right? They're polarized just means it's opposite, right? You get a north pole and a south pole, right? They're opposites of each other. You know, those are polarized thingies. And so that when I say that, what it means is that it's more positive on the outside and more negative on the inside. Okay. But there are leak channels and pumps, and these channels and pumps are able to move things against those concentrations, right? So your body will basically burn up a little bit of energy and pump a lot of stuff from one side to the other. Now it's flipped. Now it's more positive where it shouldn't be, and it's more negative where it shouldn't be, which nature's going to go, no way, put that back to normal, right? And it's going to flush it back the other way. That is happening because of leaky channels, right? So everything leaks back to where it was. So you can actually see that happening right here, right? We're going to see this action potential in action. What happens is there's some, you know, it's resting. There's nothing going on, right? But then there's some type of stimulus. Let's say it's a spider walking on your leg, right? And you start to feel like that sensation. That happened to me last night. I was just about to fall asleep, and it was not even a spider. It was literally just like something else. But I was just about to fall asleep, and I felt something like walking on my arm, and I was like, what the hell is that? And I like turned my light on and looked, and it was nothing. It was, you know, my own like blanket or whatever. And I was like, oh, you know, went back to sleep. But that is, that's, you know, something happens. There's some type of stimulus. In this case, it was a blanket brushing up against the arms, the hairs on my arm. So when that happens, the sensory neurons in my arm, right, or in the hairs on my skin, right? What happens is they sensed something which causes them to flush a whole bunch of sodium inside of the cell and a whole bunch of potassium outside of the cell. And so it flips the concentration in the opposite direction. And, you know, nature's like, get that out of here. Put that back to normal. And so it flushes it back the other way. In fact, it's actually so good at it it dips below where it was originally. And so then it has to do a little bit of work to just kind of get it back to neutral. And then that concentration gradient is restored. And so that's happening all over the place. We can see right here, right? This is more positive on the outside and more negative on the inside, right? That's the resting state. But then some type of stimulus causes those concentrations to flip, right? And this is, by the way, why I had batteries here, actually, just to keep, I kept batteries here exactly for this moment. This is actually why the batteries, in your remote won't do anything. If you put both of your batteries in a remote control like this, where both ends are facing the same way, it won't do anything because there's no way to flush positive and negative stuff back and forth. But when we do this and we set them up that way, where there's one this way and one this way, what that does is that allows electrons to be passed back and forth over and over and over and over and over again. And then the way like your remote control works basically is it sees those electrons being passed from place to place and it just steals them in order to send a signal throughout the little chip that's in there or whatever. We are officially at the end of my knowledge of electronics, but that's what electronics are. They're basically just, they create signals going back and forth, and it captures those electrons to do stuff, right? Your nervous system works this way. So what'll happen is it will restore that concentration, but at the next part of like your cell, because when the electric signal hits that, it actually causes that flushing action to happen again. And so then all of a sudden, it flips like this, right? And then it flips that way and that way. And it just constantly flips these little batteries back and forth. Nature is trying to catch up and restore concentrations back to their resting state, but then we are just sending it away and away and away, and it's traveling from place to place. And so you can see that here, right? It's depolarizing, and then it is repolarizing. So right now, this is polar. These are opposites of each other, right? But then they get flipped. That's depolarization, and it's going to travel down a neuron, right? And then nature's coming along afterwards, trying to get things back to normal, right? And it's just happening all the way from brain to, calf muscle or wherever it happens to be going, right? And so you can see there's this little signal traveling, and then it's going to jump. Like I said, it's going to jump from, like a little node to node here, because that's going to allow it to travel much, much, much faster than if it didn't have these nodes. And if you didn't have any myelin, there's a lot of fluid running throughout your body. So then that electric signal might get lost. It might travel from, into a random place. And if that happens, that's really not good. This is why myelin is such an important type of cell. So when you hear of like what's called multiple sclerosis, right, or MS, what multiple sclerosis is, it's a nervous system signal. It's a nervous system autoimmune disorder. And so normally myelin protects your cells, but unfortunately, and we don't really know why this happens, in multiple sclerosis, people's immune system, right? This system that you have that's there to like kill any foreign invaders, it starts to attack your own myelin and basically eat it away and damages your own myelin sheath. And so it's this it's kind of like rheumatoid arthritis, which is also an autoimmune disorder. Rheumatoid arthritis is where your body creates too much tissue inside of your joints, right? It thinks that it needs to create a lot of tissue. And so your immune system is basically confused. Kind of similar in MS here, except instead of like creating too much of something, it's destroying it. And so what happens is a nervous system signal will get lost. Now, luckily, there's a lot of signals like coming along in the next like step, so what'll happen is like somebody might all of a sudden lose contact with a muscle, and so that communication network gets broken, and all of a sudden their leg will give out on them. But there's another signal coming along right afterwards, so a lot of times they'll be able to catch themselves. But you'll see people with MS will have like lots of aches and pains. They'll have really poor balance. They'll have really poor coordination. They might drop something randomly, even though, they're trying to like, continue holding something. And these symptoms get worse when their temperature gets really, really high. because that makes it easier for these, signals to get lost because, it's easier for stuff to flow around in these fluids. So the only thing that we really can do for our clients with multiple sclerosis, because we don't have a cure for this, unfortunately, is we can improve their balance. So we focus a lot on teaching them how to have better balance. That way, if they do lose a connection with their nervous system for a second and then they have to catch themselves, they'll be able to. No, it does not do anything for curing the disease, but it does improve their quality of life. And then one of the other things is we have to make sure our client stays hydrated and that their tissue temperature stays relatively low. So the hotter they get, the worse their symptoms will be. And it's because basically this polarization gets lost. It gets lost because this myelin is not there to kind of protect those signals. So what'll happen is a neuron will junction with another neuron, right? It'll have a synapse, right? And so maybe an axon will meet up with the dendrite of another cell. And so you will see what will happen is that one nerve cell will release a neurotransmitter into the next nerve cell. Okay, and so that is that synaptic cleft that we talked about on Friday, right? The neurotransmitter that we often spend most of our time talking about, like I said, as trainers, like we're going to talk about acetylcholine, right? We look at that, right? Acetylcholine, which is always hard to spell, so I definitely got it wrong. We look at this acetylcholine, right? We've got a neuron here. Actually, that's not a great picture. There we go. We got a neuron here, and at the very end of it, it will release this neurotransmitter. It'll create this little sac, and then that sac will get to the end of the cell. And this only releases it when it gets hit by a certain voltage of electricity, right? That voltage being created by the action potential. And so this action potential will get down and it will release, and then that will have little receptors that will kick off an action potential in the muscle itself, and it'll do the same thing. It'll flip sodium and potassium, generating electric charge in the same way that you rubbing your socks on carpet generates static electricity, right? This is just electrochemical electricity. It's just a slightly different version, but it's all, electric signals. This is also why if you've ever been, if you've ever touched like a shock pen or been zapped by something, you contract, right? Your muscles are basically, doing, your nervous system's like, whoa, electricity just ran through us. It's why in hospital movies and stuff, you'll see them like clear, and then they go, and they zap the person, their chest jumps off the table. Their muscles are contracting in response to this electric signal. And there's other types of neurotransmitters, by the way. There's serotonin and dopamine, which are the ones that make you feel really good, or if you don't have them, make you feel nothing, which is not so great. That's what depression is. A lot of people think depression is that it's people who feel sad. That is totally an inaccurate description of this disease. Depression is basically where their brain is not either binding to or creating neurotransmitters. So it's not that they feel sad, it's that they feel nothing, which is worse, that's you'll often hear people describe it as a numbness. And that numbness is way worse. I'm sure all of us in here would rather feel sad than nothing, because that's how our brains are wired. We are meant to feel that, norepinephrine, which is a precursor to adrenaline, that's another neurotransmitter that signals things in your adrenal cortex. So, there's a lot of, and there's way more too. There's a lot of neurotransmitters out there, but they're really important for us to kind of create. So here's what we're seeing, right? Here's one neuron interacting with another neuron, and so it will release, that neurotransmitter, and then that will signal whatever type of neuron it's supposed to do. So maybe that is a neuron, signaling like happy feelings in the brain or sad feelings in the brain. Maybe it's a neuron, using the neurotransmitter acetylcholine. Maybe it's the neuron that's creating like melatonin, which is a hormone that helps you, process sleep. All of these different neurotransmitters that are doing all kinds of different things. I don't need you guys to have too much of that memorized. You'll notice that didn't really make it into our notes, but hopefully that gave you a pretty clear understanding of how these electrochemical signals actually work. Now, last thing we're going to look at here in the nervous system today, before we move on to hormones and the endocrine system and stuff, we got to look at reflexes, which reflexes are so freaking cool. I love talking about reflexes. So reflexes are really neat, right? You got to remember, your nervous system is designed to gather information, get it to the brain, and your brain is this super nerd, like your brain's like a big bookworm, nerdy guy. Anybody in here ever watched The Good Place? Anybody watch that show? It's on Netflix now, the whole thing. It's an NBC show. Andrew's in there driving, but Kenny, Charlie, you guys watch that?
No, I haven't seen it.
It is one of my all-time favorite shows. I'm obsessed.
Is that what it's a TV show? I thought it was a movie.
No, it's a TV show. It's 4 seasons. And it's only like 12 episodes a season, or like 12 or 10. And it's like 30 minutes each. So it's like there's 50 episodes from start to finish. You can kill it in no time at all. But it's all about this girl who gets into heaven by mistake. And she's like a bad person, but she's in heaven. So she's trying to like learn how to be a good person so she doesn't get caught. And so it's a lot of really fun jokes about like moral philosophy, like what makes you a good person, and there's no real answer to that question. So there's a lot of opinionated answers, which is what makes the show so funny. But anyway, the reason I bring it up is, your brain is there's this character on the show who's like the philosophy teacher, and he cannot stop overthinking about stuff because he's like, well, if I buy this tomato, is it fair trade? And like, who, farmed that tomato? Were they a good person? Like, and it's like, do they paying their workers well enough? Like, and he just constantly overthinks everything. That's what your brain is like. Your brain just constantly overthinks everything. So if you put your hand through like a metal spike by mistake, we don't want to take the time for your brain to go, okay, well, now there's a metal spike going through the hand. Should I move the hand away, or is it better to leave it there? Like, what should I do? Like, we don't want our brain to think, you place your hand on a hot stove. You don't want your brain to go, that's going to really create some damage, like, I wonder if it'll be long-term damage or it'll be short-term. Like, how fast will it, like, we don't not want our brain to like do all that work. We want to get our freaking hand off that stove, right? That's where reflexes come in. So reflexes, their job, there's all the normal structure stuff here. You've got a receptor, which is responding to some type of, detecting some type of stimulus, right? And so what'll happen is a sensory neuron will sense something and it'll travel to the nervous system. Now, normally in a normal response, it goes to the spinal cord, travels up the brain thinks about it for a second, determines what the most appropriate response is, sends that signal down the spinal cord and to an effector site, where it'll then, recruit a muscle or whatever in order to like respond to a stimulus, right? But if that signal is so intense, like a really, really big signal, like rather than touching, something cool like the plastic on this bottle here, if this thing was like, hot coffee that was, it was like 1,000 degrees and it burned the crap out of my hand, what'll happen is the sensory neurons will actually transmit from my hand, and it'll take the normal route. It'll go up the arm and then get to the spinal cord, but rather than traveling up to the brain, my spinal cord will go, nope, too big a signal, and it will try its hardest to just send a signal back as fast as possible. So then it'll get to the spinal cord, not travel up the brain, it'll just send that signal right back to whatever effector site is simplest and fastest to recruit, and it'll just drop it. Right? This is why when someone scares you, you just go, blah! And you have just like a very simple, not complicated, like whatever, I don't know, like response, right? Or when you touch something, you just jerk your hand away, right? It's a simple response. This is why reflexes are sometimes called like simple reflexes. They are fast, they're automatic, they're not meant to be like fine-tuned, complicated movements. Think of it this way. If your brain is like the CEO of a company, and you've got and it's like in charge of like all the major decisions, right? Important, nuanced decisions, right? But there is like the lead factory floor manager, right? Like he's not necessarily, he's making some decisions. He's there to like control everything, but he gets all of his orders from the brain, right? And he's walking around and all of a sudden he sees a trash can in the middle of the factory floor and it's on fire, right? He's not going to go to the CEO and be like, excuse me, boss, like knock on the door and be like, hey, there's a trash can that's about to burn the entire building down. Do you want me to put that out? Should I put that out? What do you think? Should I, go ahead and take care of this fire, right? Like instead, he's going to grab the fire extinguisher. He's going to put it out as fast as he can, as simple as possible, right? Or he's going to recruit people to put it out, right? As fast as possible. That's what a reflex is, okay? So, simple reflexes. Here's a really good example, right? You've got sensory information. This is a thumbtack or whatever, and it's intense. That's like a painful signal, right? So this is going to cause like a tearing sensation. The nerves in the finger are going to experience some type of like intense damage. So that signal is going to travel up through sensory neurons, and it's going to get to the spinal cord. But because it is such an intense response, the spinal cord is actually going to make the decision, and it will travel right back down and recruit the bicep muscle to contract the arm and pull the arm away. Okay, so that is what is called a simple reflex. Okay, simple reflexes are really rapid. They're automatic. You have no control over them. And there's a couple different types of them out there. The simple is the big term. They're very, very, think of them as simple, right? Because sometimes they get you into trouble. Sometimes you, you touch something, you pull your arm away and you smack your mom. Oh God, sorry, mom, I knew you were back there. They're very, you didn't have time to really think about things, right? So simple reflexes. Now, an example of this, it's not the only example, but the one that, applies to us a lot is a stretch reflex. So stretch reflexes are very, very simple. These are spinal reflexes, okay? So earlier when I was talking about like you're stretching and all of a sudden your thigh buckles, right? Because you start stretching too far. Simple reflexes occur at the spine rather than taking their time to travel all the way to the brain. And stretch reflexes are a really good example of that. When a muscle is rapidly stretched, the nervous system, it kind of panics, right? And so it recruits that muscle to contract, which will shorten its length and keep it from being stretched any further. So a knee jerk reflex, this is a really good example of this, right? So let's look at a knee, don't I have a picture of this? Am I crazy? Let's look at a knee jerk reaction, right? So one of the other receptors that you've got, other than just muscle spindles, you've also got Golgi tendon organs, right? And Golgi tendon organs are there to sense tension within a muscle. So when you super stretch out a muscle, right? The length of that muscle is really long, so the muscle spindle freaks out. And the tendons are being pulled apart, so the tension is also really, really high. And so that sends a signal to the brain. Now, right here, you can see this is what's called your patellar tendon, okay? And it's as your quadricep comes down and inserts onto the tibia right here, it's just below your kneecap. Now, this, if you were to stretch your thigh like this, like let's say I grab my foot like this, and then I just rip my leg back like that, right? That is really stretching out that patellar tendon, right? It's just getting really pulled end to end. And so, it can handle it because I've got pretty flexible quads, right? Not so bad. But I also did it kind of slowly. Like I grabbed it for a second, I got my balance, and I kind of moved my thigh backwards slowly. So because it went really slowly, my brain had all this time to kind of, realize, okay, we're getting longer, we're getting longer, we're getting longer. Okay, now we're getting a little long, like go and relax there, right? And so then it'll start creating maybe a pain signal or a stretch sensation, something to get me to stop stretching any further. But what if I did that signal 5,000 times faster? What if I sent the same intense signal, but I sent it at the freaking speed of light, right? Well, that's what you're seeing when your doctor tests your reflexes with this weird little hammer thing right here, right? When your doctor smacks this tendon right here underneath your kneecap, and I'm going to try and do this. I never seem to hit it just right, but if you go like this, right, you can see I did a little kick. I'm not very good at hitting it properly, but when you hit that tendon, right, with that little hammer, and you see your knee kick forward like that, right? You see that like little snap action. The reason that snap action occurred is because when you smack your Golgi tendon organ right here, you are tricking your Golgi tendon organ thinks that you just took your quad into this position here. Whoops. Into this position here at the friggin' speed of light. It thinks that you just stretched your quad muscle really, really fast. And that's dangerous, right? Moving too quickly into a stretch can tear the muscle in half. So your nervous system is designed to protect your body. So what it'll do when you smack this tendon, information goes to the spinal cord, but because it's such an intense signal, it's not going to travel up to the brain to think about. So what'll happen is it will send a signal back to recruit that quad muscle, and it'll tell the quad muscle to contract. And when your quad muscle contracts, what happens? Your knee kicks forward. So that's a spinal reflex. That's a stretch reflex, right? It's a simple spinal stretch reflex. And that one is known as the knee jerk reflex. That's the knee jerk reaction. You smack the knee and so your leg jerks forward. You've experienced this a million times, by the way, guys. We just don't think about it too often, right? If you've ever been like doing arm circles and you buckle your elbows or raise your shoulders up like this, your body finding these little paths of least resistance to kind of get this done, those are all like reflex reactions or contractions that are autonomic that you're not really thinking about. But they might not be. One of the reasons we need to pay attention to our clients' form when we're exercising is we got to be able to spot like, you're recruiting the wrong muscle right now, right? Your body's trying to find a way to keep you from stretching this muscle. So instead it's contracting that muscle that it doesn't want to stretch, and it's using this muscle instead. That's bad form, right? That's someone's knees buckling during a squat. That's someone's heels rising up off the ground while they're squatting. This is someone's shoulders elevating when they're doing push-ups. This is someone's spine sagging when they're doing a plank. All of those things are basically these paths of least resistance that help us move in a way that our body finds more comfortable, even if we're not recruiting the muscles that we're designed to be recruiting. Now, one thing I do want to mention, we can take advantage of this. We actually can take advantage of stretch reflexes in a really, really positive way. Charlie, you heard me talk about this a lot because you were in our sports mod, but Andres and Kenny, we mentioned this in physiology as well. You might remember me talking about stretch shortening cycles, right? So a stretch shortening cycle, I'm just going to look up a picture of this. So we look at a stretch shortening cycle. What will happen is, let's say somebody like sits into a squat really rapidly. When they do that, certain muscles are being stretched, right? When you go into the bottom of a squat, you are stretching certain muscles. Your quads and your glutes are in a stretched position. So what will happen is they're going to want to contract in response, right? And so then if you can manage to, as they contract in response, also like consciously and on purpose contract with that muscle, you will get some more explosive power out of it. This is where the jump cut comes from. Anybody ever do the jump cut when you're playing sports or something, and maybe you're juking somebody out and you do that thing where you jump and then you land on the ground and juke, right? If you've ever practiced jump cuts during if you've ever been in a sport where you're practicing and you do a jump and then you juke the other way, what happens is the second you land, your muscles get stretched, so then they're going to contract in response. So you contract with it and you get a little more kick off the go, right? There's a stretch reflex that happens every time your foot hits the freaking ground, but we look here, right? We can see like this is a shortened muscle for the calf, right? The calf muscle's contracting because their foot is pointed away. That's plantar flexion. But the second like their heel hits the ground, now it's in a stretched position. So it wants to go back to this. It wants to go back into a shortened position. So it stretches and then it's going to do this big explosive contraction. So what we're going to do is we are going to contract with it. That's going to give us a much more explosive reaction. This is why, we do things like depth jumps, right? They're going to start from here. He's going to land. That causes this massive, lengthening of these muscles, right? This is being lengthened. Doesn't like that. This is being lengthened. It doesn't like that. So these both want to contract. So they contract and then you contract with it. Then boom, you get a much more explosive jump off of it. And that's why, again, and I always pull this video up to show it, but the NFL players know how to do it better than anyone. NFL high jump. I mean, these are the best like high jump. I mean, they're just incredible at it because they train for it. They train to take advantage of this stretch shortening cycle. They are using simple spinal reflexes to their advantage. There's DK. All right, take a look here. So they throw their arms down. I need to play this in slow motion. Playback speed. That's the, how do I do this? Playback speed. Let's go at 25%. So they're going to throw their arms down as hard as they can. And that creates rapid stretching of the glutes and quad and calf muscles, right? And then those muscles all are having spinal reflexes because they're like, whoa, we might tear if you go any further. So they contract. Now they're going to take advantage and they're going to contract at the same time. And they're going to jump like crazy and get a whole bunch of height out of that jump, more so than they would have gotten if they just held that contraction or just jumped without, fully stretching. So we are seeing stretch reflexes happen in real time, right? And then they're all gonna kind of land. Let's see here, go back to normal speed. So the next time I try to watch YouTube, I'm not freaked out. All right. So that is our simple reflexes. They are automatic. They are, uncomplicated, and very, very, very rapid. And that is your nervous system. Any questions, guys? Feeling good? Okay, so we're going to talk a little bit about hormones here. We'll move through this, like I said, we'll move through this pretty quickly. There's about as much as NASM is going to test you on endocrine stuff. They really don't go too much into detail. But looking at hormones, right? Hormones are also under the control of your nervous system, but they act differently than your nervous system, right? Your nervous system uses electric signals to zap organs and things to do stuff, right? Hormones use chemicals to trigger things happening, right? So it's a very different process that we're seeing here. But it is under the control autonomically by your nervous system. So hormones are the chemicals. You've got a lot of endocrine glands that are creating these hormones. Your pituitary gland, thyroid, parathyroid, adrenals, pancreas, sex glands, pineal gland. There's more. You've got a whole bunch of different endocrine tissues like organs that create hormones, your stomach, your kidneys, all those things. So there's a lot of different ways that we create hormones throughout our body. And so what it is, the endocrine system is a series of glands that produce hormones in order to control bodily systems, right? So for instance, you create this hormone called ghrelin. Ghrelin is what makes you hungry. It increases your appetite. And so your stomach is growling. Well, that's because of ghrelin. Whereas leptin, which is the exact opposite of that, is a hormone that signals that you are full and satisfied. You've got adrenaline, you've got serotonin, dopamine. There's a lot of different ones out there. And so, hormones are basically these chemical messengers, right? That have certain regulatory effects on cells. One of the big ones that we're going to talk about is growth hormone, right? Growth hormone is a big part of the muscle building world. And you'll hear people take freaking growth hormone supplements, which is dangerous and totally should not be done. Because growth hormone is actually a hormone that tells your body to grow your cells. It tells your cells to replicate and reproduce and grow in size, right? And so growth hormone it's aptly named, but I wish they would relabel it and call it human stuff growing hormone, because that would give us a much better idea of how it works. A lot of people will take growth hormone as a supplement because they're like, it'll be great, it's going to give me bigger muscles. No, it's going to give you bigger everything. It causes growth in just human tissue. So it's not just your muscles, it's all of your tissues. You might end up with an enlarged pancreas, and then all of a sudden you're creating too much insulin, or maybe not enough insulin, right? And it can give you diabetes, because all of a sudden you're creating a huge pancreas, which creates lots of insulin, and that insulin becomes resistant inside of your body, the same way with someone who, has type 2 diabetes. Sometimes it'll create carpal tunnel syndrome because it grows like this little cavity inside of your wrist, and then it starts poking this nerve. Like, this is definitely a supplement we do not want to take, but boosting your growth hormone levels naturally can be a really effective way to like get good results and keep yourself young and healthy, and have a lot of really great stuff that comes along with it. And so we can do that by eating a normal healthy diet, getting plenty of sleep, and exercising. Exercising has been shown to boost growth hormone because your body goes, wow, I guess we're tearing up the body a lot. We should probably, repair that quickly. Let's create that hormone that helps us grow tissue faster, right? You've got thyroid hormone, which regulates how fast your cells are producing energy. So, anybody who's ever had like a slow thyroid, you'll often hear slow thyroid is associated with like weight control problems. A lot of people with slower thyroids often struggle with their weight. Sometimes they'll struggle feeling very sleepy. Sometimes they'll have certain depressive issues or anxieties. That's part of your thyroid. Your thyroid stimulates how fast your metabolism runs, in the same way that I was controlling my YouTube video and changing the playback speed, right? That's how your thyroid hormone works. And so you have what's called TSH, which is thyroid stimulating hormone. So your thyroid is this gland that lives on your neck. And so thyroid stimulating hormone tells your thyroid to kick out all these other hormones. This right here is what is so complicated about hormones and why they're such a pain in the butt. Your nervous system is really simple for the most part. It's like, hey, I want to do something. And so your brain goes, okay, great. And it creates an electric signal and it zaps that something. And then that something does its job, right? Pretty simple. Your hormones don't really work like that. Instead, you're like, hey, I want to do something. And your hormones go, okay, great. And so like it creates a little bit of hormone so that it can signal. And it's like, well, let me ask Bob. And then Bob will ask Terry. And then Terry will ask Sam. And then Sam will tell Jim to do this. And then Jim will get back to you, right? Like, and it goes through like 8 or 9 different steps. That's kind of how your hormones work. It's like the hormone hotline. And so, you'll create one hormone, which signals another hormone, which signals another hormone, which signals another hormone until finally what you wanted to have happen gets done. That right there is sort of why hormone disorders are so complicated. And one of the reasons why you should never take steroids or growth hormone or things like that. Because if you mess up that hormone hotline, it is very difficult to get it back to normal. And so a lot of times, like thyroid stimulating hormone, for instance, right? That is a hormone that triggers another hormone to get created. Adrenocorticotropic hormone, right? That is a hormone that gets created in order to trigger your kidneys to create adrenaline, right? Like it's a long process. And sometimes you'll experience these really dangerous things called cascade. No, I shouldn't say you. If you experience a cascade, you're in trouble. But sometimes you'll hear of things called cascades, and it's basically where one hormone gets created, and then so your body is trying to create an anti-hormone to get it to stop being created, but by the time it creates it, it was late, and so then there was a lot of it, so then it needs to make more, and it just never gets into balance, and so you'll just get these massive hormone cascades, and they're really, really, really dangerous. Again, steroids, never once, not even once. Stay away from that crap. There's series of glands that produce hormones, right? That's the system. And there's different versions of hormones out there. There's protein related ones and there's lipid related ones. Amino acid compounds, every one of your hormones is mostly made of like amino acids, and it's very protein based, except for your steroid hormones. So like your sex hormones, testosterone, estrogen, things like that, those are going to be made up of lipids. So they have like a lipid background. Again, one more reason to have plenty of protein and fats in your diet so that you can create these hormones effectively. And your body is using hormones. You'll remember back, I think on our first day of class in this course, right? We talked about the idea of negative feedback, trying to get your body back to normal. Your body will often use hormones to do that. But if it does that by mistake, if it creates too much of a hormone and it can't really get you like regulated, right? Let's say you eat like a really sugary meal and your blood sugar levels spike through the roof, your body is going to create insulin to get that sugar out of your blood. But maybe it creates too much of it, right? And so now it over creates insulin and now your blood sugar levels are too low. So then you triggers hunger hormones to be like, oh, we got to fix this problem. And then all of a sudden your blood sugar levels spike again and you have really trouble like balancing it out, right? This is why hormone regulation can be so complicated. And I just keep coming out, like, I'm just tempted to say it every time I say that. I'm like, another reason to not take steroids. And I only bring this up because trust me, guys, like people have access to steroids. They are not hard to get a hold of, and you are going to be working in gyms and people are going to be around and your clients are going to ask you about them. Just, they're dumb. Stay away. They're dangerous. They are deadly. There's so many reasons to stay away from them. And then sometimes maybe not enough of a hormone gets created. So then positive feedback kicks in. But you can see here, right? Here's negative feedback, right? Which one are we creating here? Thyroid hormone? Yeah, thyroid stimulant. So your thyroid, your brain needs your thyroid to kick something off, right? Your brain needs your body to kind of release some energy and stuff. So your brain is going to use your pituitary gland, which is the master gland that kind of controls all. And it's going to release what is called thyroid stimulating hormone. So thyroid stimulating hormone, or TSH, is going to travel down and it's going to stimulate the thyroid. And then the thyroid is going to release another hormone. And so that is going to get you back to normal, right? So the hypothalamus tells the pituitary gland to create TSH. TSH tells the thyroid to, release, whatever hormone it needs to release to kind of kick the body up into full effect. After you're done exercising, this is happening like crazy. After you're done exercising and your body temperature is like, you kind of feel warm for the rest of the day, that's thyroid stimulating hormone at work. This is why we have that EPOC, right? That excess energy burn that takes place when you leave the gym. It's going to be happening, up to 72 hours. This is why we love, exercise. It creates a really good positive hormonal response. You're basically, you're doing reps for your muscles, but you're also kind of doing reps for your little glands that are running throughout your body, and that's a good thing. So this is why you'll hear people say like, raise your hormone levels naturally through exercise. Yeah, it does happen. That's a true statement. This is one of the rare cases of true stuff that we hear on the internet that is actually like health related and true. So the pituitary gland is the master gland. This is really the main one that releases hormones that release other glands to release other hormones. It's got an anterior and a posterior lobe there. And basically it'll release like certain hormones that will, trigger those other ones off. And I'm not going to spend too much time on this, but, it creates all kinds of different ones, right? One of them it creates is called antidiuretic hormone. That's a really big one to make sure that your body is balancing your water levels. It creates oxytocin, which is my favorite hormone, by the way. I know as a trainer, I'm supposed to love testosterone, and I do. I'm a big fan. But I love oxytocin. Oxytocin, if I Google this, it should come up. Oxytocin, yeah, there we go. It is also known as the cuddle hormone. Your body will make oxytocin in response to things like hugs and, affection from your loved ones and stuff. But it's also what kind of creates like a little bit of lust there and stuff as well. So, if you've got like a crush on, if you're crushing hard on someone, right? It's because your brain released a whole bunch of oxytocin the first time you saw them. So we've got growth hormone, TSH, thyroid stimulating hormone, ACTH, adrenocorticotropic hormone, prolactin, follicle stimulating hormone. That's one that men create, in larger levels than women do, which is why we, grow body hair. Luteinizing hormone, which is helpful for building muscle. Antidiuretic hormone, which is helping with your fluid levels, and then oxytocin, which is, again, like a positive feeling one. So here's all these different glands running throughout your friggin' body. I mean, they're everywhere, right? You've got your pineal gland, your hypothalamus, your thyroid, your parathyroid, which is the back of the thyroid. Your adrenals, which actually sit on your kidneys, testes and ovaries, where we're creating our sex hormones, right? Testosterone and stuff. Look at all these places. I mean, you can see they're all just controlled. It's a big hotline, right? This sort of affects that, which affects that, which affects that. It's this big, long, very complicated route here. And so, these different lobes are controlling different things that are creating like different types of hormones. And this is another, again, like we talk about like how important testosterone is. The reason men grow type 2 muscle fibers in higher levels than women do is because we produce about 10 times as much testosterone as women do, and so then the conversation can shift a little bit, not to stray into a philosophical or political question too much here, but we look at like the idea of like, one of the reasons why like gender norms have become like or not gender norms, but just like the conversation around like gender has gotten really complicated in the last few years. I think one of the reasons it's so complicated is because of a fairly large understanding of how hormones work. Like, we look at like certain like women who have extremely high testosterone levels or men who have extremely high estrogen levels. That is literally sort of resulting in a different like this idea of like gender, right? Like, don't get me wrong, like you've got your sex parts and stuff that you're born with naturally, but like, if you blast any of us in this, I mean, this is a call full of guys, you blast any of us with massive levels of estrogen and turn off our levels of testosterone, it will result in like different characteristics. That follicle stimulating hormone will reduce and we'll have less body hair. We will see like less testosterone. We'll start to see a loss of type 2 muscle fibers, right? It does literally have very tangible changes in your body, which is why I like the idea of like labeling someone based on like their, outer characteristics is a pretty flawed way of like, basing this idea. And also like only testing for like hormone levels is also a pretty flawed way of looking at it, right? That's much more related to the conversation around sex than it is around like the idea of like someone's like gender. And that's what's very interesting about hormones. They have a very tangible effect. Now, again, one more time here, I just want to mention how steroids work. Steroids, which are basically massive amounts of testosterone, which is what you're taking. That's what steroids are. When you talk about like steroids, they're testosterone injections, right? And so what that does is it floods your system with very, very, very high levels of testosterone, which your body goes, whoa, this is more testosterone than we are used to having. So what it does is it turns off your normal testosterone production. And so your testes literally stop producing their own testosterone. And then what happens when you stop taking those steroids is you are creating only testosterone, and your body is like, I'm sorry, it was having massive levels of testosterone. So then you stop taking those steroids, and so then your body has no testosterone, and you start to experience like you start to manifest female traits. This is where you hear of what is called gynomastia, where men will start to experience like a growth of breast tissue. And that is a response to low testosterone levels. And you're like, wait a minute, they were taking steroids. Shouldn't they have really high testosterone levels? Yeah, absolutely. But once you stop taking it, your body is in response creating estrogen to balance you back to normal, and it is turning your normal testosterone levels off. This is why athletes who are using steroids have to take what they call it post-cycle therapy, which is basically where they will take testosterone boosting stuff to get their normal levels, and they'll take like estrogen blockers. That's how A-Rod got caught. It is very difficult to catch someone who is taking steroids. It is really easy to catch someone who is taking post-steroid therapy. That's how most athletes get caught. They don't usually get caught while they're on steroids. They get caught afterwards. That's how A-Rod got caught. That's how Mark McGuire got caught. It's a name I haven't said in forever. Mark McGuire just came out of my head. haven't thought about that guy in years. I hated him when I was a kid because he was in the home run race with like Sammy Sosa and Griffey and stuff. And Sosa and McGuire both got caught for steroids, and Griffey never did. And I remember just being just furious as a kid. Anyway, sorry. So these are this is the conversation around like those types of hormones and why they're so dangerous and why they're banned in pro sports, because they do lead to these really negative health effects, really, really, really negative stuff that affects us in very bad ways. Now, don't get me wrong, like, you guys want to get into the philosophy of things. I will say, and this is a very controversial opinion that I have sometimes, because I'm all about, like, I'm a purist when it comes to sports. Like, I want to play the original version of the sport. I don't want to mess around with the rules and change that. I want to play, what it is, and I want it to be an even team. Like this whole Astros thing that happened last year. In my opinion, like, no one won the World Series that year. They should just remove that title. And there was no World Series in that year, because they cheated, and people, and like some people are like, they got fined and stuff, and I'm like, yeah, they shouldn't be allowed to play baseball again. Like, people are like, oh, that's so harsh, and I'm like, no, they wanted to play a different version of baseball. They don't get to play the original version. Like, I feel the same way about steroids. You get caught doing steroids, you're done forever. Ever. Like, you wanted to play a different version, you go do that. Now, that being said, do I think it would be really cool if we had an entire steroid league? Like, maybe it would be kind of cool to see how someone launch a baseball into space, but there's my controversial, you guys can think about that for the rest of the day and judge me. So, all right, looking at the rest of our hormones here, just kind of knocking the rest of these out. So we've got some really interesting ones, part of your thyroid. You've got what's called thyroxine and triiodothyronine. Is that what it is? No. I can never say it. Triiodothyronine. That's what it is. This one's regulating your metabolism. This one's really huge right here in terms of like protein metabolism. And this one's really important in terms of like metabolic rate. So when you hear about somebody who's like, that person who's like kind of bouncy, they're creating a lot of thyroxine. We know that person who has a pretty easy time like developing like their, building muscle, they have a lot of T3. There's calcitonin, which is regulating, this is a big one actually. Calcitonin is huge. This is regulating your bone growth. And so we'll see, like, they'll test for your vitamin D levels, and they'll also like test for calcitonin in your blood. Your adrenal glands, which live on top of your kidneys, that's helping amp up body systems, right? So creating adrenaline and things like that. Epinephrine, that's your fight or flight hormone, right? Again, this goes back to that, sympathetic nervous system. Your body will release epinephrine. That's the big thing to remember here. Your endocrine system also controls stuff just like your nervous system does, but it does it through hormones instead of doing it through electric signals. There's the pancreas, which creates, insulin and glucagon. Insulin's job is to pull sugar out of your blood. Glucagon's job is to release glycogen into your blood as sugar and raise your levels back to normal. So you can see that right here. We've got diabetes, which is obviously a disorder where the pancreas isn't working the way it's supposed to. Either type 1, where your pancreas just doesn't work very well, or type 2, where your pancreas is working fine, but your cells have actually become resistant to it, which is not good. And then, like I said, you've got your androgen hormones like testosterone, dihydrotestosterone. Your ovaries like estrogen and progesterone and things like that. And that's all I got for you guys on hormones. Just these are kind of your key vocabulary terms. A hormone is a chemical messenger. It's created by glands. And then the big one is your pituitary gland, which creates the, sort of kicks off the whole thing. It's the master gland. All right. Any questions on any of that, guys? Kenny, Andres, Charlie, you guys feeling good today?
Yes, sir.
All good today.
Cool. All right. Well, I'll kill the recording and see you guys tomorrow.